Hi, my name is Dulce Ordaz, and I'm gonna explain my argumentative exam. We are gonna start from the time-independent Schrödinger equation in a one-dimension quantum well. As we can see here, we have our equation number one, where we have that our target variables are the energy and the psi, that it's our wave function. As we can see here, we have our reduced Planck constant and the effective mass, which is a multiple of the effective electron mass. We can say that inside the well, the electrons are stationary because they don't move, and that's why in the time-independent Schrödinger equation we don't use the time. Inside the equation, we can see that we have the potential energy, and inside the infinite quantum well, the potential is defined as between the interval that we define from 0 to 8, that is the width of the well, it's equal to 0 and infinite outside the well, as we can say something like that. And as I said, the interval of the well it's from 0 to 8, so the potential turns into 0. So we can quit this part of the equation, and we have this. Now we simplify the equation, and this is equivalently as this one because we are talking about a second derivative. And next we have to solve numerically. So we have to make like the steps to solving the equation, like the derivative. So we need to make the delta x, that is the well, inside divided by the subinterval n plus 1, which are all of equal length. And our read points we have here like this, and I explain them like, for example, first my interval will be n plus 1, so it is 0 plus 1, 0, and 1 plus 1 delta x. And I can state this part of the intervals like this. X n plus 1 is equal to a, that is the width of the well. And then, well, this one is not so useful right now in this part of the equation, but help us to understand what is happening and how the derivatives work. And now we can introduce the central finite difference approximation. And with this method, we obtain an equation system, which can be solved using the eigenvalues and eigenvectors. We have this, that is an approximation. Also, it is important to say that also in this side of the equation, there are plus delta x, but we can simply ignore that values because they are neglectable, because they are very small values. That's why we are talking about an approximation in this part. And then going with the second derivative of psi, we can replace this equation right here, as we can see here. So we have a multiplication of these constants that are constants inside the well from this part. And now placing outside of the brackets the delta x squared. This is because delta x is the domain of the problem, which is in the x-axis, so it is a constant. Then we have the following. We put outside the constants, and then we put the negative sign inside the bracket. So we have this, but as we can see, um, the negative signs also affected the index, as we can see here. Now we'll start with the negative, put the past, present, the future. And then we have to set the boundary conditions that are in c of x, that it's equal to 0. When we are at 0 and a, our boundary condition is equal to 0, which in the straight form is psi 0 is equal to 0 and psi n plus 1 is equal to 0. This means that the interior points, all the sides are unknowns. Well, this can be said as follows. In the walls of the well, the boundary conditions are equal to 0, but inside, all these ones are unknowns, like in an equation. So for understand this, I set an example where we have three interior points. that is I equal to 1, I equal to 2, and I equal to 3. I simply substitute the I in, well, I is equal in n of n, equal to n in this part. And we have these equations, but in this part, we simply ignore the psi equal to 0 and psi equal to 4 because these ones can be seen that they are outside of the matrix. So we simply don't put them in the matrix. So our matrix will start from 2 and then follows minus 1 and then follows a 0 because this column can be seen as a psi 1, psi 2, and psi 3 because our three integral points are equal to 3. So our matrix is a square matrix because it's 3 times 3. So, well, I state this in here, where psi 4 is equal to 0 and crosses the border of the well due to the statement psi n plus 1 equal to 0. Then I rearrange the matrix so we have that these constants times our matrix full of these elements times our C1, C2, C3. We see it here that it's an equation system as we said in the last part. And this is equal to the energy times the, the unknowns. Also, this can be seen in the linear algebra as the A lambda equals A equals our eigenvectors equal lambda times our eigenvectors. But in this case, as we're talking about the Schrödinger equation, our Hamiltonian is our matrix of coefficients times our constants. And our wave function of psi are our eigenvalues, or our eigenvector. And the problem reduces to this. Hamiltonian times psi times energy times psi. We can see here that the Hamiltonian matrix, which is a square matrix, tridiagonal, and symmetric, its transpose is the same as H. Nice. Okay. The psi is our eigenvector of no wave function values, and our energy are our eigenvalues. Now going to the statement of the problem, we have to choose our target wavelength. The light color is determined by its wavelength lambda and related to the photon energy, as we can see here. For my design, I choose color yellow, which has a wavelength of 580 nanometers and a related photon energy of 2.14 electronvolts. This is because the arsenide of gallium, which is a material of the semiconductor, has a band gap of 424 electronvolts. So the color yellow, which was selected, is realistic for my design. In a quantum well, the inertia can be estimated as this equation, which is an approximation. Well, it's here important to say that this value can be obtained using this matrix. Well, this problem reduced from the Schrödinger equation. And also, this part of the first heavy hole, it's obtained by multiplying our first eigenvalue times 0.15, which is also an approximation. Now, well, also an analytical way of obtaining our first eigenvalue can be this, using our E lambda times the energy gap, band gap. And also we have these formulas that were used in my MATLAB code. Also, it is important to say that I use the last formulas to compare the implement matrix model, as we can state here, where the Hamiltonian H for a weld of 10 nanometers, and then I change it to 3 nanometers. I'm going to explain this part, and I use 100 interior points. Now going to my MATLAB code, well, I'm going to show my MATLAB code. First, I decided to choose 10 nanometers width of the well because in the class we saw an example of 10 nanometers with where the professor told us that the first eigenvalue is approximately 0.05 as we can see here. So I decided to choose that width to see how accurate my code is. Then I put the effective mass of the gallium arsenide and I choose my interior points and the energy levels. Then the radius Planck's constant, these ones are the constants that we already know. But it's important to say that to use the mass, we have to multiply our effective mass times the electron rest mass and the conversion from joules to electrovolts. Then I use a loop to use this part of well, to use the Hamiltonian and our matrices that we state in the problem. I did my equal space intervals. Well, already, actually, I use them. I said that no, but I use them in the code. And then I put my tridiagonal matrix inside the Hamiltonian. The main diagonal that it's full of twos, and my other two diagonals that are in the sides of the twos that are full of -1. And I sum up my three matrices. And then I obtain the Hamiltonian multiplying the constant times my matrix. So now I can obtain my eigenvalues using this command of h times EV. I did this because my Planck constant is in joules, so I have to convert them to electrovolts. And then I put them in the ascending order because otherwise the program wouldn't know if I'm doing the max value or the less of the minimum value. And this is my loop. And then, as I said, I use the color yellow. So this is the photon energy of yellow and the gallium arsenide band gap. Then I call my first eigenvalue, that is also known as the first electron energy level, obtained by the eigenvalues. And then I decided to make a comparison between the eigenvalue obtained of the first energy level with an analytical solution that is stating here. We solve this formula in class. And also I use the first level that is equal to 1. And then also using the formula of lambda of yellow means the band gap divided by 1.15. I also make another comparison from my eigenvalue, the analytical solution, and the target eigenvalue, that it's the first electron energy level. Well, this is an extra point that I did, that it's obtaining the heavy hole energy level, but this whole also help us to understand if my eigenvalue that I've calculated, it's accurate because my E lambda calculated needs to be equal to my lambda yellow, so my program will be correct. And then we have here my matrix, and I obtain these values. As we can see, with the well of width of 10 nanometers, I required 0.6 electrovolts in the first level, but I obtained a 0.056 electrovolts also in the analytical solution. And my total emission energy is 1.4, that it's so different from the 2.1. But I make an extra calculation to see what's the well width that I needed to my program to be accurate. So my program will be accurate. And I use this formula that we saw in this part here to obtain the correct well width. And I obtained 3 nanometers. That's what I say, that I first used 10 nanometers and then I use 3 nanometers. And the only thing that I did was changing the well width with 3 nanometers. Everything it's the same because I use the same color. I use the same, well, actually, everything is the same, yes. And yes, we can see here that with 3 nanometers, the first eigenvalue is 0.6. The the required, the or also called as the target. My first eigenvalue used obtained with the Hamiltonian is also 0.6, and the analytic is 0.6. So I'm correct in this part. And then obtaining the total emission energy is 2.14, that it's equal to the target emission energy. So now my code is correct. But the exam asks us to iteratively adjust the wall width A until my computed first electron energy level gives an emission wavelength close to my chosen lambda. That's what I create an while and true statement, which is for the iteration loop. Look, the first values are the same because, well, also I use the 10 nanometers to make this part of the iteration where my program repeats till I get the correct well width. And the mass, effective mass is the same, the intervals are the same, the levels are also the same. Everything is same, but as we can see here, now I'll put like the analytical solution first. And then I set up my loop parameters. The maximum iterations that I used was 50. So my program will stop endlessly if I don't put this while loop, but my program will stop till the 50 iterations. And my counter is set to 0, so this will start from 0, 1, 2, 3. And I put a tolerance because if the tolerance is closer from if the error is close to the tolerance, my program or the loop will stop. I start the increase iteration counter by 1. The quality space interval, again the matrices from the Hamiltonian. And now multiplying this one to obtain the Hamiltonian. This one is the same as the last code. And now I join the two line codes in one to make it smaller. I obtain again my first eigenvalue, that it's my first electron energy level. And then I compute the error, that it's my obtained eigenvalue, that it's my first electron energy level, minus my target, so I can see the error. And the loop will repeat till the error gets closer and closer, till I get the value of the tolerance. And I put here, I explain this as if the absolute error is smaller than the tolerance, the loop will stop. And if the maximum number of iterations is reached, my program will stop no matter if I reach the desired well width. And then I update the well width for the next iteration. As we can see here, I have this formula, but I explain this formula in here because it's not something that it's very clear to obtain. First, oh, wait a minute, it's here. I have this formula that it's like an analytical approach with the number of levels that we choose. First, I choose for simplicity, I choose the energy level number 1. So, here was P. I will correct that. And ignoring this part and the two constants that are to M, I have this equation this proportionality, where we can see that if the well gets smaller, in other words, A, the energy increases, but if the well gets bigger, the energy decreases. Then I put my variables that I use in the program, if the analytic energy computed, and my current well width, that it's like the all well width, and the energy target, that it's my desired energy level that corresponds to the yellow emission wavelength. As we can see, are the same formulas, but the well width is the one that changed. And I make the radio. So because even though in MATLAB we're not using these formulas, in this case, it is the best way to obtain the well width because it is implicit on it. To get the new width, it is necessary to take the radio. So I have these ones, and I eliminate the ones that are the constants. And with the sandwich law, I obtain this part and then I have to clear for the new well width. And I have this, and then I with the square and I get a square root, and I obtain this. And this part of the code is the one that I use in my MATLAB code, because not using this line of the code at MATLAB makes the loop infinite. In other words, the 50 iterations are used and the accurate well width is not obtained. Now going back to my MATLAB code, again I make an analytical approach, the heavy hole energy level to obtain the total emission in a gallium arsenide quantum well. And we can see here that two iterations were obtained with the first well with the obtained eigenvalue, the target energy level, and the error that we obtained. We see at the second iteration the error is close to the tolerance, so the program stops here. And after two iterations, my well width is 3.002 nanometers. My target energy level is 0.6. The one that I obtained with the eigenvalue, it's also 0.6. Analytical approach, it's 0.6 as well. And we can see that the total emission energy in this, how can I say it? Well, in this new code, it's equal to 2.14, also the decimals. So now we can say that to obtain a wavelength equal to the yellow color, the well width need to be equal to 3.002 nanometers with 100 intervals inside them and 3 levels of energy. Well, in this part, I decided to join to mix the analytical part with the eigenvalues part with the target energy level, because I can compare three different operations in one same space, so I can see how accurate and correct is my program. And also it is important to say that obtain the total emission energy in each step, I use the eigenvalue obtained of the Hamiltonian. And that's all. Thank you.